Hey class, today we're going to go over something called the gas laws. Now we talked a little bit about gases if you took your freshman science class with me, and so some of these things might sound a little bit familiar, but we're going to go over them because they lead into more complex concepts later on in the lesson. One thing to know about the gas laws is we're going to be working with algebraic math, so it shouldn't be hopefully too difficult. So what are the gas laws? There are four variables that are needed to define the physical condition or state of a gas. Those four is temperature, pressure, volume, and the amount of gas that we express in moles. The equations that express these relationships between all four of these variables are called the gas laws. There are three that we're going to talk about today, and the first we're going to talk about is Boyle's law. This is a pressure-volume relationship, which means it's going to compare those two variables. In Boyle's law, it states that as the volume of the gas decreases, the pressure is going to increase and vice versa. That is only true if the temperature and the amount of gas remains constant. For example, if we double the pressure, it's going to cause the volume to decrease in half. And we call that type of relationship inversely proportional. Again, all that means is if one goes up, the other goes down. Or if one goes down, the other goes up. Now we actually apply Boyle's law every time we breathe. And the way that we do this is the rib cage can expand and contract. And the diaphragm is what's going to control the volume within your lungs. And so when we inhale, which we know as breathing in, and then we have exhaling, which is breathing out. So what actually happens during these two stages? Well, when you breathe in, your rib cage can expand, and when it does this, the diaphragm moves downward. Because of this, the volume within your chest cavity increases. This is going to cause your pressure to decrease. And this change results in air rushing in. Now, why would air rush in when the pressure decreases? I want to make sure that you guys add this to your notes. Pressure will always travel from high to low. So if you decrease the pressure within your lungs, that gives it lower pressure, and so air is going to travel to that lower pressure. Now when we breathe out, it's going to be the opposite. Our rib cage is now going to contract and our diaphragm moves up. The volume then decreases, which causes the pressure to increase. And because we have increased or high pressure within our lungs, again, air is always going to travel from high to low. So it's actually going to cause air to rush out. I've also included this image right here in our lesson to show what does the diaphragm look like when it's contracting or when it's relaxing. And so here in the first image, this is inhaling or breathing in. We see that when the diaphragm contracts, again, it flattens out. This creates more volume within the chest cavity, and just like we put on the previous slide, pressure is going to then decrease. Whereas when we exhale, look in this picture, the diaphragm actually relaxes and it prevents you from having as much volume, so your volume ends up decreasing and therefore pressure increases and air flows out. For Boyle's law, we actually use the following equation, P1 times V1 equals P2 times V2. And in this equation, P stands for pressure, and then V is going to stand for volume. Now, what does this 1 and 2 mean? 1 is usually going to mean before any changes, or if you hear the words initially, or it started at, or original. That is always going to be plugged in for P1 or V1. If you ever see a 2, that usually is going to mean after. So what did you end with after the change? We have a sample problem here to use this equation. It says a container of 4 liters of carbon dioxide has a pressure of 1.5 atms. If the original pressure was 0.9 atmospheres, what was the original volume? So I always tell people, make sure you guys list your variables and then kind of, oops, that's supposed to be P2, and then plug in what you know. So here I saw the word original and it says my original pressure was 0.9. So that means this is going to be plugged in for P1. And it's asking what is the original volume. So again, original before means it's a 1, so that's going to get an X. From there, we're going to plug in our other values. For P2, it's going to be 1.5, and then for V2, it's going to be about 4 liters. Now that we have all our variables listed, we can plug it into our equation. So we get 0.9 times X equals 1.5 times 4. We're going to use our algebra to solve from here. 0.9x equals 6. Divide by the number attached to x, and then we end up getting x equals 6.666 repeating. Because we're doing chemistry math, we want to make sure to round to the correct number of sig figs, and so our lowest number of sig figs here is 2 from our 0.90, so we're going to round this to 6.7. From there, we have to figure out our units. What's really nice about these problems is that our volume units are attached and our pressure units are attached. So if my original volume, if we're trying to find that, we can look at the volume of what we ended at, which was 4 liters. So that means my original volume must be in liters as well. The next type of relationship we're going to look at is a temperature-volume relationship, and this is usually summarized in Charles' law. Charles' law states that temperature and volume are directly proportional, and that is true if pressure and the amount of gas is constant. So what does it mean to be directly proportional? It basically means if one of those values increases, the other is going to do the same thing. And vice versa. If one of those values decrease, the other value is going to decrease as well. Our equation for Charles' law is V1 divided by T1 equals V2 divided by T2. Again, same thing. V is going to be our volume, T is going to be our temperature, 1 is going to be before the change, and 2 is going to be after the change. The only thing that we really have to keep an eye out on is that temperature has to be in kelvins. Now, most of the equations that I'm ever going to give you is I'm either going to give it to you in Celsius or give it to you in Kelvin. If I give it to you in Celsius, you must use this first equation by taking the number I give you and adding 273.15. Now, college typically uses the 0.15. However, in the past, I've always let my classes use 273 if they wanted to as well. I have answer keys that have both answers if you use 273 versus if you use 273.15. Usually the answers aren't really off by a whole lot. I also included the second equation in case you were ever given something in Fahrenheit, but I do not believe that I did that. We're going to look at an example of Charles' law. Again, we're going to look at the equation. Remember, our equation is V1 divided by T1 equals V2 divided by T2. Just like any problem, I always have everybody list the variables and then kind of plug in what we know. So it says the temperature inside my refrigerator is about 4 degrees Celsius. If I place a balloon in my fridge that initially has a temperature of 22 and a volume of 0.5. So that word initially is going to mean, well, that's what I started with. So that's going to be my ones. So that means my temperature was originally 22 and my volume was originally 0.5. Now then it's asking what will be the volume of the balloon when it is fully cooled by my refrigerator. So since it's asking what will be the volume, that is going to be my X. And so then we have to figure out, well, what temperature is that fridge? And it says it is 4 degrees. Now, oftentimes people take these and then they try to solve, but just like we stated on the previous slide, the temperature must be in kelvins. If we look at this problem, our temperature is in degrees Celsius. So what we're going to do is we're going to add 273.15 to each of these in order to change my degree Celsius into degree Kelvin. So we get our initial temp as 295.15, and then we get our final temp as 277.15. Now that we've changed everything into Kelvin, we can actually go ahead and plug in and solve just like normal. 0.5x divided by 295.15 equals x divided by 277.15. Oftentimes, when we have a setup like this, I always tell people to cross multiply and divide. So here, what we're going to do is we're going to take 0.5 and we're actually going to times that by 277.15. When we do that, we get 138.575. And then we're going to take the 295.15 and we're going to times it by x. We get 295.15x. We're going to divide by our number attached to x. And then when we do that, x actually ends up coming to be about 0.4695 with other numbers. Again, we must round to the correct number of sig figs. If we look at the problem, our lowest number is 3 based on this value and this value. So we're going to actually round to 0.470. Now we just have to figure out what unit I'm going to give it. Just like the last one, our volumes are going to have the same unit and our temps are going to have the same unit. Because my original volume was 0.5 liters, that means my volume after the change must also, again, be in liters. The last one that we're going to look at is a quantity-volume relationship called Avogadro's law. Now, before we get to Avogadro's law, we're going to talk about Avogadro's hypothesis. And this states that equal volumes of gases at the same temperature and pressure contain equal number of molecules. And all that means is if you had 22.4 liters of any gas at, let's say, 0 degrees Celsius and 1 atm, it's always going to contain 6.02 times 10 to the 23rd gas molecules. And again, that should sound familiar because that was the number that we learned as being Avogadro's number. Now, because of this information, he created something called Avogadro's law that states the volume of a gas maintained at constant temperature and pressure. So again, temperature and pressure does not change. The volume is directly proportional to moles. And so again, directly proportional, all that means is if one increases, so does the other. That also means if one decreases, so does the other as well. And so our law equation is going to be V1 divided by N1 equals V2 divided by N2. N is always going to be equal to the number of moles. So I'm going to make a note here, and I would make a note in your notes as well. If you are given grams, so if given grams, you must change, you must change to moles using molar mass. If it's already in moles, then you don't really have to do anything. The other thing, again, I want to point out is V stands for volume, N is moles, 1 again is before the change, and then 2 again is after the change. So we're going to do an example here. Again, our equation is V1 divided by N1 equals V2 divided by N2. Just like any problem, we're going to list our variables. Our problem says a sample of gas occupies 2 liters with 5 moles present. What would happen to the volume if the number of moles is increased to 10? So here we see words that indicate that there's going to be a change. It's going to increase to 10. So 10 would actually be my final number of moles. And since it's asking what would happen to the volume after that change, my volume for V2 is going to get X. From there, we can see that 2 liters would be my initial volume and 5 moles would be my initial number of moles. We can actually take these numbers and plug it into our equation. 2 divided by 5 equals x divided by 10. Just like our previous sample, we're going to cross multiply and divide. So 2 times 10 actually gets me 20. 5 times x gets me 5x. We're going to divide by our attached number to x, and we end up getting 4. Now, because our sig figs, we want to make sure we have those. Even though it's 4, I should have 3 sig figs based on my values. So we want to keep the same place value, so this would be 4.00. Just like any problem, our units are attached, so volume units must be the same as well as moles. Since my initial volume was 2 liters, that means here my unit must also be liters since I'm still looking at volume. So 4 liters would be my final answer. And that's the end of today's lesson. If you have any questions, please let me know, and I hope you guys have a great day.